All right. So welcome back, and it's my pleasure to be back again, this time bringing you a session on building fault-tolerant applications. For those who is watching this session on the live streaming over the web, this is going to be a session focused on the best practices of building fault-tolerant applications. You can follow this irrespective of whether you're in the hall or you're watching it on the live stream. Okay, so this session is based on a very popular white paper written by my colleagues. It's called Building Fault-Tolerant Applications on AWS. This is accessible at aws.amazon.com/whitepapers. It's a very well-received white paper, and I'm going to touch upon a subset of the topics that are discussed in this white paper. So let me get started. The agenda for this session is to take a closer look at the AWS building blocks, then take a look at Amazon EC2 architecture with focus on specific elements like AMI, Elastic IP, Elastic Block Store, and Elastic Load Balancer. Then we'll briefly touch upon the high availability features of Amazon RDS. We'll revisit the concept of multi-AZ that we have heard in the morning. So let me get started. Typically, irrespective of whether you are deploying your application on one server or on a cluster or even on the cloud, you're going to have two layers of the stack. The topmost layer is going to be your application. The bottommost is going to be the physical infrastructure, whether it is one server or a global infrastructure like Amazon Web Services. And even on the cloud, this will not change much. You still have pretty much the same layered architecture of hosting your application and talking to the underlying resources. But in between your application and the actual physical infrastructure, there are many other layers that offer you various levels of abstractions and also value additions. So let's take a closer look at the big picture of Amazon Web Services. You have seen this before, but I want to spend a little bit of time on each of this. To develop any meaningful application, you need servers, you need storage, you need a little bit of security and networking, and then you need databases. So they actually form the infrastructure building blocks for Amazon Web Services. These are the fundamental building blocks. You can use them independently. For example, we know customers leveraging only Amazon S3 for their backup and archival purposes. And of course, we see many customers using just Amazon EC2 without any other services. It's a very classic use case. You can also use database alone as a service through Amazon RDS. But the best thing is you can actually consume them as one, or you can consume all of them together and come out with very interesting scenarios. That's the reason why they can be compared to Lego blocks. They come in different sizes, different shapes. You connect them in a way to form a unique shape that makes sense to you. That is your use case. So many customers leverage the same building blocks, but they derive a very different architecture from this by connecting them in different ways. So these are the foundational building blocks which form the most important layer in the architecture. Then we abstract it a little bit and offer more value-added services. For example, on S3, we actually offer content delivery in the form of Amazon CloudFront. Of course, you can also have the content coming from custom origin, but typically S3 and CloudFront work very well in conjunction. Similarly, when we have utility computing, it makes sense to offer parallel processing in the form of hosted MapReduce, which is called Elastic MapReduce. Similarly, when we have the underlying network infrastructure, we can give you an asynchronous messaging mechanism through SQS and a notification service called SNS, Simple Notification Service, and the recent addition, which is Amazon Simple Email Service, or SCS. So these are the services that are built on top of our existing building blocks. And then we have further levels of abstraction as we go on the stack. You need security. Security is our number one priority. You heard this multiple times, but how can you really leverage security that we have embedded into AWS? You can do that by using multi-factor authentication that comes with the AWS Management Console during the sign-up process. You can also make cloud resources available in a very granular way by leveraging a security concept called Identity and Access Management on the cloud, which is IAM. And of course, we have a monitoring service which will work in conjunction with a set of services like SQS, SNS, EC2, ELB, auto scale, and so on. That's called CloudWatch, which is a platform to monitor, track, and visualize the performance metrics of your resources. And to make it easy for developers and administrators, we also expose a platform layer called Amazon Elastic Beanstalk, which will hide away the complexity of dealing with virtual servers, storage, databases, and so on, particularly for the developers, where they can deploy their applications with one click from Eclipse or even from other IDEs. Similarly, for IT administrators, we offer a layer called CloudFormation, which will help them describe the layout and topology and the resources in a declarative way. So that's CloudFormation. Again, it's not a standalone layer. It leverages many of these blocks that you see. And of course, finally, the way you deal with the entire cloud infrastructure is from one of these interfaces. Many developers actually use the web interface. The libraries, developers use libraries. And many operations professionals will leverage web interface. And of course, we have various plugins, as I mentioned, for Visual Studio and for Eclipse, and command line interfaces for IT administrators to integrate their scripts and so on. And your application ultimately sits on top of this, consuming the services in one of the forms, right? So this is a big picture of Amazon Web Services. Now, with that in place, let me walk you through the most important service of AWS called EC2, the most popular, most highly consumed service. This is a flexible compute capacity on the cloud. It is flexible because you can start very small and you can grow as big as you want. And it is resizable, as in you can scale up, you can scale out, you can scale down or scale in based on your scenarios very easily, and you can automate most of these operations. And like many of the services and the promise of AWS, it's inexpensive, starts with zero capex, and it offers you pay-as-you-go model. Extremely secure because we have instance isolation at the bottommost layer of the stack. So that's the quick overview of EC2. But I want you to understand this in a little different way. So let me walk you through the typical initialization of an EC2 instance. As an architect, developer, or an IT professional, or an operations person, your fundamental interaction with AWS will start in choosing the right region. That's the number one choice that you are going to make. It depends on where your customers will ultimately come from. Do they come from Americas? Do they come from Europe or Asia Pacific? And based on that, you're going to make a choice of region, right? In the morning, we have discussed this multiple times. We have about 6 regions, and you can deploy your resources in any of the regions. So it all starts with choosing the right region. Once you decide on that, then choosing the right template in the form of an Amazon machine image is the next important step. Think of AMI as a pre-defined and pre-configured server template. You want a Linux virtual instance, you want a Windows-based one, you want a FreeBSD, you want OpenSolaris, or you want a CentOS or a SUSE Linux. You can choose from a variety of operating systems, and the processor architecture in terms of 32-bit or 64-bit, and that decision happens in the second phase, right? So once you have the AMI chosen, then you are going to launch that as an instance in one of the availability zones. So as I mentioned earlier, availability zone is a distinct isolated facility within a region offering you a lot of redundancy and high availability. You might want to choose a specific availability zone and ultimately launch your AMI as an EC2 instance in an availability zone. This is the fundamental interaction that you will ever have with EC2. That's not all. You need to be familiar with a couple of more concepts. For example, every instance comes with a local instance store, which is called ephemeral storage. So ephemeral storage is the inbuilt storage that comes by default with every instance. But the life of this ephemeral storage is directly proportional to the life of the instance. Once you terminate the instance, the ephemeral storage ceases to exist. It's a part of the instance that you are going to deal with. Now, to take your data beyond the typical life cycle of an EC2 instance, you will attach a cloud drive or a disk in the cloud in the form of Elastic Block Store. This will enable you to go beyond the typical life cycle of an instance and persist your data for a longer time. And if you want to make it much more redundant, you can take a snapshot and occasionally put that snapshot on S3. So that's going to make it much more foolproof, because you can have multiple snapshots which are point-in-time snapshots, and you can store them on S3. Once you have this, you'll obviously want to create a security group, which is like a firewall. And once you have the firewall in place, then you will go ahead and attach an elastic IP, which is going to offer you a level of redirection. And once you have this, you can automatically enable monitoring. We have the default monitoring and a detailed monitoring. Detailed monitoring is going to offer you performance metrics up to a granularity of 1 minute. So you can actually, you can actually get a granular visualization of the performance metrics through Amazon CloudWatch. And then you can also launch multiple instances in the same process and put them behind an elastic load balancer. Once you have this, you can connect the CloudWatch performance metrics with the EC2 instance using an auto-scale policy, which will define how often and when the instances should come up and should be brought down. So this is the big picture of EC2. If you are able to follow what I mentioned, and if you are able to identify each of these blocks and understand how they function, you know most of the EC2 by now, because this is the big picture of Amazon Elastic Compute Cloud, right? Now it's time for me to take each of these components and drill down further. Let me start with an elastic IP. As I mentioned earlier, every time you launch an instance, it comes with a public DNS name, which you cannot control, which you cannot make it persistent. So the public DNS name of an EC2 instance is based on the region that you are launching, the IP address that it's going to be assigned, and you have no control over it. So every time you stop and start an instance, or every time you relaunch an instance, you will get a different endpoint. That's not very easy for you to deal with when you are going live and in the production environments. So how do you make sure that your domain names, which are typically, let's call a hypothetical portal, gadgetshop.in, and I want to point that to a specific EC2 instance. So I introduced an intermediary, which is called elastic IP, which is a public static IP address, and my domain's CNAME gets pointed to this elastic IP, and this elastic IP points to an EC2 instance. And the advantage I have is I can swap this instance at any point without really touching my actual DNS and the public IP address. And you can do it even on the fly. For example, if you face issues with a specific instance, bring in another healthy instance and quickly wire the elastic IP to talk to the healthy instance. And this is going to be extremely seamless. So I want to give you a visualization of how this works, and then we go into a live demo, rather a demo, not a live demo. So this is how you're going to attach an elastic IP address to an EC2 instance. And as you notice, the EC2 instance is currently running a web server and a database server in the form of Apache and MySQL. After a while, for some reason, if the performance of your EC2 instance degrades, it can happen for various reasons, you can quickly bring in another. That's it. Okay. So yeah, it has become stateless component. So now you have an elastic IP address that's pointing to a healthier instance, and this is going to be absolutely seamless. So let me show you a series of steps of achieving this. Now this is the EC2 console, and as you notice, I have a primary server and a secondary server. Let's call it Shop Web Server. It's an e-commerce portal that I have built. And when I access the public DNS name, it looks something like this. You have AP Southeast 1 followed by or preceded by an IP address. It's very hard to remember. But you can copy and paste it in the browser to see your website in action, right? Now, this is nothing great. This is how most of the EC2 instances are anyways accessed. But now what I'm going to do is to click on the elastic IP link in the navigation bar and click on allocate new address, grab a public IP address from the pool of allowed IP addresses, and this is called elastic IP. It's called elastic because you can keep switching the actual endpoint at runtime. So once you have the elastic IP, you can associate that with a primary instance, which we have already identified here. And after that, the instance ID is associated, and now I can access the same website using the elastic IP. Okay? Now you have another layer that isolates your domain name and your actual web server. Now let's go ahead and actually stop this instance. Okay, this is my way of emulating a degradation in the virtual instance. So I'm going to stop this, come back to the browser, okay, and do a refresh to see a 404 error. Obvious, because the web server is dead, it's not responding anymore. Now I want to associate this degraded primary web server to a secondary one. So now I am going to initiate this process and wire it up with my secondary server, which is more healthy. And then just do a refresh, and the website is back in action. Okay? Is this the best way? There are many other things that you got to do, but this is the first line of defense. Never ever launch a production EC2 server without an elastic IP address, without at least 2 instances running. That too preferably in multiple availability zones. Because if something happens with your primary server, you can always rewire the traffic via the elastic IP to a healthy instance running in another availability zone. Okay? It makes sense, but that's not all. There is a fundamental issue with this approach. Static websites are great, but an e-commerce portal has to deal with transactions, shopping cart, payments, and you cannot afford to lose the data. The fundamental flaw with our design here is we are running the database and the web server in the same box, and if the box goes down, your database is inaccessible and you lose all the transactions. Elastic IP is only meant for redirection. So how do I make sure that the database is available even after the termination of an EC2 instance? How do I achieve that? Well, that's where the EBS comes in, Elastic Block Store, which can be created anywhere from 1 GB to 1 TB, can be formatted with a native file system, all the way from NTFS to ext_f3 or any other even encrypted file system of your choice. And it's automatically replicated within the same availability zone. So we offer you redundancy, and in case of any host failures, it automatically gets recovered for you without you even initiating it. And you can of course take point-in-time snapshots, keep them on S3, and recreate your entire EBS volume on demand when you want it. And you can also monitor certain parameters related to EBS within CloudWatch, the disk IO related metrics. Now, we go back to the same architecture where we have an elastic IP wired to an EC2 instance, and now we attach an elastic block store and move the web server and the database server to the elastic block store. Now this offers us a second layer of protection. In this case, if our primary server goes down for some reason and becomes inaccessible, we bring up another generic web server and a database server instance, and we plug in this drive, and we make the database and website pointed to the new elastic block store. Another refresh, you get back to the same state, because the EBS has the up to minute logs and the data files related to MySQL. It also has the latest build of website that can be pointed from the web server and database server, and it gives you a chance to quickly rewire up to minute transactions, right? So let's go ahead and see a demo. Again, I start off with at least 2 instances, preferably deployed in separate availability zones, and it's accessible, great. Now what I'm going to do is to go ahead and create a new drive on the cloud, a new disk on the cloud. So I click on create volume button, that brings up a dialog where you can define the size and you can choose an availability zone. One important aspect is you cannot create an elastic block store in another availability zone than your EC2 instance, because the IO is going to be very expensive, very heavy, so they got to be in the same availability zone. So make sure that the EC2 instance that you're going to attach this to and the EBS are in the same availability zone. Once I make sure that everything is in place, I go ahead and create, and you notice that the 1 GB volume is now available. In the next step, I'm going to attach this to the primary server, and I'm going to make it available as a device at /dev/SDF. And now we are going to log on to the console. So I'm now logging on to the primary web server as root user. I become a sudo root user very quickly. Then I'm going to do 2 steps. Step 1 is to move my website. Step 2 is to move my database, right? So first thing, I stop my, even before that, even before we get there, we need to make sure that the EBS volume is formatted and mounted, right? This is step 0. We cannot afford to miss this. So I'm going to create the file system on this device and then quickly mount it by running mount command and make sure it is mounted properly. So now it's available. So this is step 0, right? Formatting and mounting the device. After that, we are going to stop the website, the Apache web server, and then run bunch of commands. Don't worry if you're not able to follow this, particularly if you come from the Windows side of the world and it looks very, very technical, don't bother. But this step is essentially about taking your existing website and relocating that to the newly created EBS volume. So I do it for HTTPD etc and www directory. Then I create links to both these and restart Apache web server. So now you have successfully moved the website from local instance store to EBS. Then we do the same thing with MySQL. First we stop MySQL, then we create appropriate directories for data files as well as logs, and we relocate the latest up to minute, up to second logs and database files to EBS. Then we run some administrative commands to take ownership, and finally edit the my.conf file where we comment out the original data directory location and point it to the new location which is located on the EBS volume. We do the same thing for log, point it to the EBS directory. That's it. Come back and start MySQL, and now go back to the browser and do a refresh. Technically, it doesn't make any difference. It's just that the website is getting served from a different volume. The database has been successfully moved to another volume. Technically, we haven't made any changes to the architecture. But now comes in the expected thing, an issue with the instance. So I go ahead and force this instance to be stopped and do a refresh on the browser to CF404. Now the challenge is not only getting back the original website, which we have seen in the previous step, but getting back the original transactions. So now I forcefully detach the volume from the degraded instance. I detach it, and now it becomes available all over again, and attach it to the secondary instance, which is running and which is healthy. And once this is created, we go back and just access the secondary instance. Remember, the secondary instance doesn't run the latest website or the latest database. It just has Apache running, it just has plain vanilla MySQL running. Doesn't have anything beyond that. That's why you will see the default landing page of Apache. Now we log into the instance, quickly become the root user. Don't format the Elastic Block Store, but quickly mount it using the mkdir and mount commands. And now if you do an ls, you'll notice that it has the website and the database successfully relocated, available, up to minute information. Now we do the same thing. We first stop Apache and we rename the existing directories and point the directories from the Elastic Block Store to Apache, start it again. That's it. Now you have created a link from the local directories to EBS, so you have just wired your latest build of website to Apache. Then we do the same thing with MySQL. We stop the service, we open the conf file, do exactly what we have done with the original server, point it to the EBS directories, save it, come back to the command prompt, start MySQL again. Go back to the browser, do a refresh, and you'll go live, right? And it gives you up to minute information because the database has been persistent and is available even after the termination or unavailability of an instance. This is the second line of defense, right? I hope you are able to follow this. So first was Elastic IP, the second is Elastic Block Store. Now comes in a very interesting, slightly advanced technique. It's called instance metadata. Before we jump to the demo, I want to spend some time quickly giving you the context, particularly for folks who are very new and who are not familiar with EC2 environment. Let me set the context here. The cloud works very differently. I touched upon that concept in the morning. On the cloud, you don't have the luxury of hardwiring and hard coding your connection strings, endpoints, database, server names, IP addresses. Everything is dynamic. Everything is dynamic. The analogy that I normally give is, it's driving your own car versus getting a taxi. When you actually call up a cab company and ask for a car, you don't have a choice of the number, the car number that you will get, right? You cannot control. You call Meru Cabs and you cannot say, look, I am very, very superstitious. I am going for an interview. Please send me a cab whose number tallies down to 4. It's my lucky number. Do you think the cab company will really send you that because you believe in it? No. You got to compromise and you got to get into any cab with any number plate. The same thing happens on the cloud. You ask for a large instance, AWS gives you a large instance, but you cannot say, give me this instance with specific IP address and make this permanent. Unless you attach it to an elastic IP, you never get that. But elastic IP is public, and the private IP address is something that you don't control. So every time you reconfigure, relaunch, reboot, you have to deal with a new set of endpoints, new set of configurations, and so on. It's a very stateless environment. So how do you deal with it? And actually speaking, this is not specific to cloud. This is how SOA is typically leveraged by many enterprises. You never hardwire anything, never hard code anything. Typically in the architectural world, developers are familiar with concepts like registry, right? If you are coming from the Windows side of the world, you know what a registry is. Then you know what is Active Directory meant for. And for the folks who are coming from Java background, there is something called JNDI and property files, where you isolate and you abstract out the information which will be populated at runtime. But on the cloud, there is no registry. Of course, you can build one, but there is no ready-made registry that you can go look up. You can emulate it by using a variety of techniques. But imagine this entire dynamic world of instances popping up, databases popping up, and they got to talk to each other and quickly perform a task in the most cohesive way. It's very, very difficult. So I want to give you an example here. This is very applicable to a scenario where an application is running on spot instances. You know how spot instances work, right? So spot instances are EC2 instances where there is no fixed price. You bid for the compute power that's available, and when the bid is won by you, you automatically get to instantiate n number of instances, and they keep running as long as your bid is still the winning bid. The moment you lose the bid, that is someone else has won the bid, which is slightly higher than yours, the instances automatically get shut down. You don't get any choice of taking a backup or performing a cleanup, nothing. They just go into a sleep mode. They are shut down, right? So when you're dealing with an environment like spot instances, you cannot afford to have instances that are pre-bundled and which can come up and figure out everything and perform a task. They should be extremely stateless, dynamic, and self-aware. For example, let's say I'm running a task of converting multiple number of text files to PDF, right? And I don't really bother how often this process is going to be initiated and how long it's going to take. I have a time limit of, let's say, 1 week. In 1 week, I want to convert n number of text files to PDFs, and I have precisely written an application environment that actually works in that way. An instance comes up and asks, who am I today? And you will tell the instance that today you are a PDF processor. Then the instance will say, where is the input coming from? And you will point it to an input queue. Then it says, okay, I know who I am, I know where the input is coming from, what is a processing application that I should run? Then you'll actually populate a script. It says, great, I know where it is coming from, I know who I am, I know what to do, but ultimately where do I put the output? You will point that to another queue, which is going to be the output queue. Once you have this information created or populated within an AMI, you can make AMI extremely dynamic. The way it works is, this is the EC2 environment, the gray box. An EC2 instance comes up, and it doesn't have any registry here, but within the EC2 environment, we actually expose an endpoint called 169.254.169.254. This is like a well-known endpoint. This is the location that every EC2 instance will have access to. Now, the EC2 instance will send a request to this endpoint saying, who am I? That comes with a lot of data. It might even answer, who am I, what am I supposed to do, and why am I here? You can actually send answers to all these questions by populating that endpoint with a custom metadata. Once this metadata comes back to EC2 instance, you can parse it, and for example, in our case, when this EC2 instance queries this endpoint, we tell that, hey, EC2 instance, today you are a web server. And the next question is, if I am the web server, where is the latest website code? Where is the build? Then you say, it's available in this S3 bucket. Now the EC2 instance will make a connection to S3, pulls the latest website code, reconfigures itself, and goes live, attaches itself to an elastic IP, and everything is taken care of. Right? Again, this is exactly how you can parallelize. That's the reason why I took the example of Mumbai Dabbawalas in the morning, where you never know what that instance is going to do when it is just booted, when it is just launched. After the warm-up period is over, you can actually instruct that to do a specific job. I want to give you a much more realistic scenario. For example, in our architecture, we have a master database and multiple slaves. And I have a reason for connecting one web server to a specific database server in a specific pattern. Now, on the cloud, you never know where the database server is going to be instantiated. Of course, you have control over region and availability zone, but you never know what is the IP address it's going to get and so on. So the database instances come up and publish their information into a well-known location. You grab that and you populate your EC2 instances metadata and you wire them up. So how do you do that? Let me give you an example. So I first create a very simple text file, a comma delimited string, comma separated string. Let's call them hypothetically DBS1, DBS2, and DBS3. This will be populated dynamically after the database servers come up. So we are just assuming these are the connection strings, but they get actually grabbed after the database servers are alive. Now, once that is captured, we launch an EC2 instance with the standard EC2 run instances command. Everything else remains very conventional, very standard set of parameters, but -f followed by user data is an additional metric that you will use, additional parameter that you'll use to send the user metadata, user data to the instance. And after this, the instances come up. Each of them query this 169.254.169.254, figure out what is the connection string, and once they are available, if you access each of these servers, you notice that the instance number is 0 and the database server is talking to DBS1, right? Now you grab the second public DNS name of the server, you access it to notice that it is talking to slave 2. The same thing for server 3, it talks to DBS3, right? And if you are wondering what is the PHP code, it's extremely simple. There is nothing very complex here. I just use file get contents function to query this endpoint, which is AMI launch index. Now this gives me an array of the number of instances that I have created. Typically, if I have launched 4, the array is going to be of 4 elements, starts with 0. So it gives me an ability to capture the launch index of the current instance. Then I parse the user data, which is a comma separated value. And now, based on the index, I'm going to access each of the elements. What that step really means is server 0 will talk to database 1. Server 1 will talk to database server 2, and so on. So these 3 lines or 4 lines of code essentially does that. And after that, it becomes very dynamic for me to wire up database servers with the EC2 instances. Now, if you are not very clear about it, catch me after this session. I can walk you through many more scenarios where this is used. But this is extremely useful in creating a dynamic environment on the cloud. Okay, then comes in Elastic Load Balancer, another very important aspect of making your applications fault tolerant. ELB or Elastic Load Balancer does 2 things really well, and that's what it is meant for. Number 1, the most obvious, routing the traffic across a fleet of EC2 instances in a highly optimized fashion. Number 1, that's the job of the load balancer. But beyond that, it also does another thing very, very well, that is tracking the health of the instances. Now, why is that useful? If the ELB is not intelligent enough, it will keep routing the traffic to a dead instance, and occasionally some of your users will see 500 server errors or 404 errors. Not a great idea. But ELB is extremely intelligent. It can route traffic only if the instance is reporting to be healthy, right? So to summarize, it does load balancing, of course, very well, but it also does the monitoring of the health and diverting the traffic to healthy instances. So it makes a lot of sense to see the demo based on what we have discussed previously. We have the same 3 web servers running. Let's call them shop web server 1, shop web server 2 and 3, and they are launched using the metadata. So they are talking to a specific database server. And now I'm going to create a load balancer, right? And we point port 80 of the ELB to port 80 of the EC2 instance. And this is a very important step. Basically, the ping protocol is HTTP, and it's going to ping index.php, right? That's the parameter that I define. But how long should it do it? So it's going to check once in every 30 seconds or half a minute. And when it is doing it, if there is no response for more than 5 seconds, it may call it unhealthy. And if that happens for more than 2 times, it will really mark it unhealthy, and the traffic will not be diverted, right? So these are the parameters that will define how the ELB should define the health of the instance, right? So ping every 30 seconds and wait for 5 seconds. If there is no response for at least 2 times, mark it unhealthy. And if the last consecutive 10 pings have been successful, then bring it back as healthy. This is what you are defining here. So it's a very, very simple way, but very effective in keeping a tab on the health of your EC2 instance. Once we define the health parameters, we can choose the number of instances here. For example, all these instances should be added. In our case, I have launched them in the same availability zone, but ideally you should launch them in multiple availability zones to balance the traffic. Then we add all of them, we review the settings once, and go ahead and create the load balancer. After which you grab the A record of this, wire it up with your domain, and go live. Once you, by the way, it takes a cooldown period, few minutes to really register all the EC2 instances into ELB. That's why initially it will show the status as out of service, but eventually it will become in service, indicating that all the servers are now registered successfully with the ELB. Now you grab this and directly access it in the browser, not using a specific EC2 instance DNS name, but actually using the ELB name, the DNS name. Now, if I constantly refresh, you'll notice that I have deliberately written out the connection string and the instance launch index. You'll notice that it's going to vary between 0, 1, and 2, because these are the number of servers or instances that we have launched. So this is ELB in action. I wish I could do a live demo, but unfortunately, the cloud is only as strong as the internet connection we have. So I made sure that I've captured the screenshots. So that will give you a quick idea on how to set up an ELB and make your application more fault tolerant. That brings us towards the last topic of this session, which is RDS. So as we discussed earlier, RDS offers you a database plus database operations on AWS. So it gives you an opportunity to launch MySQL or Oracle database without going through the hassles of really setting up and configuring and launching and managing. You got to be a DBA to deal with databases. But in RDS, you need not be a DBA. You request for an RDS instance, you only define the required parameters, and the database gets provisioned to you. And as a developer, what do you need from a database? An endpoint and CRUD operations on it. That's it. You can treat that like a black box service. That's exactly what RDS is. So in RDS, you can choose to launch your database, particularly MySQL. This is applicable only to MySQL, in a multi-AZ mode, where RDS will provision a primary server in one AZ and the standby in another AZ, and it enables synchronous replication with minimal lag. In case of a failure with your primary, the RDS infrastructure will promote the standby to the primary, and the endpoint still remains the same. That means the connection string still remains the same. You are not going to touch your client application at any point. And once this automatic failover happens, the client application will continue to talk to your database like the normal way. And after a while, the primary gets fixed and it gets into the standby mode, and the replication will again start till the point that it is up to date, and this process will just repeat in the future, right? So this offers you a unique advantage of failover without you really configuring anything. It's a checkbox option, or rather a drop-down option. So you have seen this earlier. Now I have already created a multi-AZ database for our e-commerce portal called Gadget Shop. So you just need to select an existing database, say modify, and choose the appropriate multi-AZ flag. Just turn it to yes, and it now gets deployed into multi-AZ as is, right? Cool. So that brings us towards the end of this session. It was, I know we covered quite a few concepts in a very short span of time, but the idea is to give you various various mechanisms and line of defense to deal with your fault-tolerant applications on the cloud. So to summarize, start with EC2. I should mention, start with at least 2 EC2 instances, minimum 2 instances deployed in multiple availability zones. Then go for an elastic IP. Don't forget to create and attach an elastic block store, extremely critical. Then learn how to bundle generic EMIs and deal with the instance metadata. If you are scaling out and you have a lot of traffic coming in, you can associate EC2 instances with ELB and enable health monitoring, not exactly monitoring, but tracking for health and routing the traffic appropriately. And if you are dealing with RDS, don't forget to launch it in a multi-AZ mode, right? So these are the resources. Obviously, you can visit EC2/EBS and /RDS URLs on aws.amazon.com. You can learn a lot about these services and also download the Getting Started guides and various other resources. So that brings us towards the end of the first session.